All right, so we're going to be solving a projectile motion problem. The problem is where a projectile is launched at 10 meters per second at an angle of 53.13 degrees above the horizontal. We want to find the following three things. How long will it be in the air? How far will it go? And what is its maximum height? We're going to assume that it's being launched from a position of 0, and it's going to go up, come back down, and come back to the same 0 position. So it's not being launched up to a cliff and not being launched down from a cliff or anything like that. Next, I would like to point out that we have these 4 equations. And the top equation, in fact, the top 3 are the kinematic equations. The bottom one here is known as the range equation. So we have the 3 kinematic equations of x equals x naught plus v naught t plus 1/2 at squared. The x is the final position. X naught is the initial position at time 0. V naught is the original or initial velocity. Acceleration is going to wind up being acceleration in our case, but it doesn't always have to be. And t is the time where at time t it's going to be at position x, not x naught, but position x, the instantaneous position. And then if I go to the next equation, I can go through that one as well. So v is the final velocity. V naught is the initial velocity at time 0. Again, you have your acceleration that's occurring, and after that acceleration occurring for an amount of time t, it will have a velocity of v. So the first thing I want to do here is make a triangle that's going to represent my initial velocities. So I'm going to make my first vector, and I'm going to try and make it about 53 degrees. So if this is 45, I'm going to go up a little bit, and it's going to be about the 53. It's maybe a little bigger than that, but that's okay. And then I'm going to draw the x and y components of it. And so there we go. That's not too bad. I have my v naught, my initial velocity, which is equal to 10 meters per second. And then in the x component, I'm going to have an initial velocity in the x direction, and I'm going to have an initial velocity in the y direction. And I'm going to have some values for those that I'll find. Now keep in mind that this entire triangle represents initial velocity. Every part of it represents initial velocity. The moment when it is launched, it has an initial velocity of 10 meters per second along its angled path. But at that same moment, we can look at its velocity in the x direction. And that same moment, we can look at its velocity in the y direction. So to find those velocities, I can scroll down a bit. And what I should probably do at this point is perhaps look at what those velocities are, looking at cosine and sine. So for the x direction, we're going to look at the cosine of angle theta times my velocity, my initial velocity. That's going to equal the initial velocity in the x direction. And it'll wind up being the same thing except using sine for the y direction. So we'll use sine of angle theta times the initial velocity. That will give us the initial velocity in the y direction. And so those values will be 8 meters per second for the y direction, and it will be 6 meters per second for the x direction. And always try and keep your units. All right, so let's see if I can maybe shrink this down and give myself more space, or just move it up a little bit. There we go. So I've got a little bit more space. Now, what I'd like to do next is to put down what information is given. So if I look at the x and y direction, when I want to solve for how long will it be in the air, I need to look at the y component. So it's very important that I look at only the y component now. Now that I've broken it up into its x and y components, for gravity, gravity only affects the vertical, the y component. So let's take a look at that for a moment. So y naught, meaning the initial y position, is going to be equal to 0. I'm going to write down everything that I know. Y is also going to equal 0 because I want to know how long it's going to take to leave from the 0 position, go up, and then come back down. And that's going to be measured in meters in both cases. the velocity, the initial velocity in the y direction, is equal to the 8 meters per second. The acceleration, and that's going to be the acceleration of gravity specifically, is equal to a negative 9.8 meters per second squared in this case. And if I extend my page a little, t is equal to, well, I don't know. But what I do know is that what I'd like to do, ideally, is find an equation that has all of those variables in it, and only those variables in it. One of them can be an unknown, and the rest can be known. I don't need to necessarily have all of them, for example, with y naught or y. Since they're 0, I don't necessarily need them to be in the equation. But regardless, I can certainly find an equation that has them, and that is going to be y equals y naught plus v naught t plus 1/2 at squared. And that's going to be v naught in the y direction specifically. This is a linear equation, meaning that I can only take into account one dimension of space, one direction at a time. So it's going to be the vertical direction. Now I want to solve for t. And the first thing that I should do is I should realize that I have these values here of 0 for both of the y's. So what that means is I'm going to have 0 equals 0 plus all the rest of this, but now I can factor out a t. So I have t, and then parentheses, v naught in the y direction plus 1/2 at. I'll close my parentheses. And so in order for this statement to be true, either one of these things, either this t either will equal 0, or this will equal 0. Either one of those two things equaling 0 will make that formula true. So that means that there's two answers. There are two answers for time. T is equal to 0, which is true, because at time 0, what is its position? 0. But the other solution, we must go from here. So 0 is equal to v naught in the y direction plus 1/2 at squared. And from here, we're going to solve for time. And so let me scroll a little bit so that we have some space to work. And solving for time, I'm going to wind up having, it'll turn into negative 2 v naught in the y direction over a, and that will equal t. All right, so I can plug my values in, and that's going to wind up being the negative 2 times the initial velocity in the y direction, which is the 8 meters per second, over the negative 9.8 meters per second squared. And that will give us a value. And in fact, you know what, before I even get into what the value there is, let me make a small change. Let me change the units a little bit. Let's see, that's not supposed to happen now, is it? There we go. Meters per second per second. I'm going to write the units that way instead of meters per second squared. And the reason is I want you to show that there is the meters per second will cancel out, and we'll be left with time. So the dimensional analysis here is going to work. So this will give us a value of 1.632, and that will be seconds. Now that I've found how long it's going to be in the air, it's going to go up and come back down. It's going to take 1.632 seconds to do that. Well, now keep in mind that time, it's relatively dimensionless in that it doesn't go into any particular direction. It's a scalar quantity, actually. So the time it takes for it to go up and down is the same time it takes for it to go left and right. It's the same in both. So I get to use that now. Let me work over here where I have the velocity in the x direction is equal to the displacement in the x direction. So the delta x over the time elapsed. And so my time elapsed is 1.632, and my velocity in the x direction, if I go back up, I had shown that it is the 6 meters per second in the x direction for my triangle. So as I come back down, I have velocity in the x direction times time is equal to the change in x. So 6 meters per second times a time of 1.632 seconds. The seconds will cancel out, and I'm left with meters. And this will give us a value of approximately 9. Actually, there's no approximation now, is there? It's 9.792. And that's going to be meters. All right, now I found answers for the first two parts. I found the time it's going to take, and I found the x displacement, the x direction displacement. I would actually like to show you that I can find that x displacement in a different way. Now, for now, I would rather you not do it this way, but I do want to show you the use of this equation, the range equation. So let me write that down. We have the range, or the x direction displacement, is going to be equal to the initial velocity squared. Now notice that that's not in the x direction or y direction. That is simply along its path, times sine of 2 theta over g. And if you also take notice that this equation has theta in it. So that right there should tell you that this is not a linear equation, that it can take into account the fact that there's 2 dimensions occurring here. And really all I have to do is plug in my values and solve for r. That's all I really need to do in this equation. So doing that, I have r equals, v naught is my 10 meters per second, and that's squared, times sine, the sine of 2 times theta, which is the 53.13 degrees, and that's all over 9.8 meters per second squared. And notice I did not put a negative sign in there, because whenever you have an equation that has g, you simply put a positive value for the acceleration of gravity. Now, if I do this the long way, I get, on the top, I'm going to get a total of 96. My units, well, if I look, let me show you where I'm looking. If I look here, 10 meters per second, and that whole thing is going to get squared. The units get squared as well, so that will be 100 meters squared over seconds squared. And then the sine 2 times 53.13 degrees, that's not really any units there. It's just a coefficient. The degrees is just a coefficient. So that does not affect my units. And that will turn this into 96 meters squared over seconds squared. But what if I write it like this? Meters times meters over seconds squared. And I'm doing that because on the bottom I still have my 9.8 meters per second squared. And if you notice that one of the meters cancels out, the seconds squared cancel out, and I'm left with meters. So again, I'm just showing you the dimensional analysis. And for a final answer here, I am going to get a 9.796, and that is, again, meters. And so what I'd like to do is focus in on that for a second and compare that to what I got just a moment ago. I can have them both on my screen. Here's the other one. And they are virtually the same. In fact, this one here is more accurate because there was less rounding involved in that case. So that's the one I'm going to use going forward, but either one would certainly be acceptable. And in fact, I would rather you learn how to do it this way because, well, the other one is just so simple. You need to learn how to break it down into its components and understand what's really happening there. So let's move along. Now, the last thing we have to find is, if we go back up, we have to find how far will it go and what is its maximum height. That's the last thing we need to find, is what is its maximum height. So I'm going to write uh, maximum height as y max. That's how I'm going to denote it, the y displacement max. So that's instantaneously where is it going to be at its highest point. And for an equation on that, I'm going to use v squared equals v naught squared plus 2a, and it will be y max minus y naught. I don't know why. Quit asking. See, it's a joke. Why not? So as you can see, if I'm going to solve for y max, and really it's y max minus y naught, it will turn into, let's see, one very crucially important thing is that for the y max, v is going to be 0. The final velocity, it's going to be 0 because it's when it comes up to a stop as it's at its highest point. So with that in mind, let's finish that off. So we have v naught is going to equal. Oh, I'm sorry. No, I want to solve for y max. My apologies. So v naught squared over 2a is equal to y max. There we go. And we're going to plug and chug our values in. So we have v naught in the, I almost forgot here that I need to put a y here. Don't let me forget that. So this is going to be velocity in the y direction, initial velocity in the y direction there. And that's important to remember because, again, we're back to a linear equation where it's just the vertical. And so since the vertical initial velocity was 8 meters per second, and that's going to get squared over 2 times a negative 9.8, so times a negative 9.8 meters per second squared, and that's going to equal my y max, and that in turn will give me a value of 3,000, excuse me, not 3,000, 3.265. Now be careful about your parentheses here that you are applying your parentheses correctly, because otherwise you would get some very large number if you just put it in your calculator without using any parentheses. So we have 3.65, oh, and that's meters of maximum height. That's the maximum height off the ground it will reach. And I would like to show you one last thing, if I can. I would like to go back to the range equation. The range equation being the, I'll just rewrite it, the r equals v naught squared times sine of 2 theta over g. Okay, and what I'd like to show you is I'd like to kind of go back and prove the angle that it was shot at. So I'm going to put in my values that I got for my initial velocity. I'm going to put in my range. I'm going to put in my range. So what I'd like to do first is to rearrange this equation so that way I solve for theta. And so firstly, I'm going to multiply each side by g. So rg over v naught squared. And keep in mind that that's just v naught, not in along its path, not in the y or the x direction. That is just the regular v naught. That's the 10 meters per second. And that in turn will equal sine 2 theta. And I'm stopping there for a moment just because I want you to look at it. This is where a lot of mistakes happen. The next thing I need to do is take the inverse sine of both sides, then I divide by 2. What I see happen a lot is people divide by 2, then take the inverse sine, and you can't do that. So let's take the inverse sine of each side. I have the inverse sine of rg over v naught squared, and then all of that over 2 equals angle theta. Let me put that in, put the values in. So I've got the inverse sine And see, the range that I'm going to use is the 9.796 meters. That's the range that I got, times the 9.8 meters per second squared. And remember, that's going to be positive because it's a g in the equation. And that's going to be all over the initial velocity squared. That's the 10 meters per second. And we're going to square that value. And all of this will give us an angle of 36.8707 degrees. And at first, you might be thinking, wait, that's the wrong angle. When we go back up, we had an angle of 53.13 degrees. And that's not the angle that we just came up with. So what's wrong? Well, nothing. What we've done is we've found the reflection upon 45 degrees. See, when we have something being shot at 45 degrees, that is going to be its farthest path. If you shoot an object at, let's say, 50 degrees, it's going to go some path and fall shorter than that. The farthest you can go is 45 degrees. So if I go 5 degrees higher, I'm going to hit some spot. And if I go, and that'd be 50 degrees, if I go 5 degrees lower at 40 degrees, I'm going to hit the same spot. So there's another angle. If I can get rid of this. There's another angle. So what I do is I take 90 degrees minus the 36.8707 degrees, and that will give me a value of the 53, transpose the numbers, a value of 53.1293. And quite obviously, that's awfully close to 53.13 degrees. So that just kind of shows a little bit of rounding errors that we had along the way, but really did a pretty good job of not making that too bad. So I just wanted to go back and show you how we come up with those angles. And so there's always going to be two angles that will hit the same spot. One will go high, one will go low. Hopefully this was helpful. Remember to break it down into its x and y components. Find the time it's in the air, and then from there you can look at the x component and find the range. So the biggest mistake I see is people putting in to the equations up here. Let's say I pick out this equation here. What I see a little too often is for the V naught. Let's say this one here, the V naught, in the y direction. We need to put the V naught in the y direction. But all too often, I see people putting in the V naught along its path, and we cannot do that because this is an equation that I can only take into account one dimension at a time. So please be careful of that mistake, and good luck. Thanks for watching.